Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Right. Good afternoon. We're happy to have Shirshendu Ganguly tell us about competitive erosion.
Thank you, Yuval. So I'll be talking about something called competitive erosion, which is a competing particle system on graphs, and the talk will be based on joint work with Lionel, Yuval, and Jim. And Okay, so all right, so first the model. So to define, like I said, it's a competing particle system. So you have two kinds of particles, and you have some interaction. And so to define the process, you need some underlying data. So what do you need? So you need a finite graph G. I mean, like, it does not have to be finite. So you need some graph G, say with vertex set V and E, and the edge set E, and you need two probability measures mu1 and mu2 on the set of vertices. So you have a graph, you have two measures mu1 and mu2 on the set of vertices, and you need an integer k between 1 and, so suppose the graph has size n, then you need an integer between 1 and say n minus 1. So you have a graph, you have two measures, and you have a number k. And formally, this process will be a Markov chain on all k subsets of the vertex set. So you have this graph V, you have this number k, so you look at all subsets of V of size k, and formally this process is going to be a Markov chain on this state space. So to define this, so I need to define how to get ST. So ST was my process, so I need to define how to get ST plus 1 from ST. So it's, I'm like, this is what we are going to do for the rest of the talk. So think of all the vertices as having like two colors, red and blue. And so k was my size of ST, so think of ST being the set of blue vertices. So there are k vertices are going to be blue, and the rest of them are going to be red. And so I have to define how to get ST plus 1 from ST. So what I do is, so ST has size k. So what I do is I add one point, which is xt, and I subtract one point, which is yt. I'll define what those are. Okay, so yeah, so first I have to add one point xt. So I have these two measures mu1 and mu2. So what I do is I start a random walk on the graph with initial starting distribution mu1, and then I wait till it hits this complement of ST. So ST has size k, I start my random walk and look at the first site, which is now red, which it hits, and that I include in my set ST. So ST union xt is now a set of size k plus 1. And now I have to like subtract of one more element to get the right size. So I have this other measure that I can still work with, which is mu2. So I start a random walk with initial distribution mu2 and like wait till it hits the existing set of size k plus 1, all the blue vertices, and then at the first site that it hits, I remove it. So I have k, I added one point, it became k plus 1, and then I removed another point. So I'm back to the set of size k. And so this was introduced by Jim in around 2003, and so I'll come back to some of the motivations later. So there will be an example which will make this definition clear. But okay, so here is a very basic graph of size 6, and k is 3. So all the blue vertices are the set ST, and now in this example, mu1 and mu2, which were my starting distributions, are just point masses at these 2 points. So think of this as mu2 and think of this as mu1. So first I start a random walk from mu1, so it does some random walk, so it picks this edge, so it's already hitting ST complement in the first step, so I make this blue. So 3 became 4, and then I have to like start one more random walk from here. Suppose it picked this edge, so it's still on the red cluster, and then in the next step it hits the blue side, so this will turn red. And so in one step I went from this configuration to this configuration, so the number of blue points remained the same, but they moved around a bit. So is the definition clear of the process? Okay, good. So this was a very general example, and now we will sort of see an example of a graph which we will really care about during this talk. And so this is a disk of radius 30, and every vertex is colored independently red and blue with probability 1/3, and so number of reds is 2/3 fraction of the total vertices. So every vertex is colored blue or red with probability 1/3 and 2/3 independently.
be more than 2 colors there.
I mean, so there are some shading issues. Yeah. So
It's an artifact.
yeah. So it's some pixel thing. And my mu1 and mu2 are, for this example, just the point North Pole and the South Pole. So my blue random walk will start from, so think of this as in the complex plane, and if this is the unit disk, it will start from -I, and the red random walk will start from I. Okay, so let's see how this looks. So you see there is some, the blue vortices are getting accumulated near the blue source, and the red ones are getting accumulated near the red source, and we'll run for some time. So let me go ahead. Okay, so yeah, so you see that they have come close to each other, and okay, of course there's some particles here which are still yet to be colored red, but now they're done, and so you have this like two different regions of blue and red, and then this is boundary or interface between them, and it's sort of like not very deviating, like it's roughly smooth. Of course, the size is just 30, so if you make it more and more, then you will see even smoother pictures. So the interface is not very fluctuating, and also you see what the shape of the interface is like, right? So you can already guess what this looks like. There's some fluctuations, but roughly it's not a straight line. Roughly looks like an orthogonal circular arc, right? It might be clear, might not be, but okay, so good. So this was the general example. Then we saw the example on the disk, and now some background and motivation. So there is some similarities with the very, very basic fundamental growth model, which is known as the internal DLA, where there's just one particle involved. So you have a graph, and you just try to see how a set of particles sort of grow with time. So you just have this one version. So IT is your cluster at time t, and to get IT plus 1 from IT, you now have just one distribution mu1. You start a random walk with distribution mu1, and you wait till it exits the cluster IT. You have one more point that you add to your site. So at time t, the size of the cluster is exactly t. So you keep growing by 1 at every time step. Okay. And so this was first proposed by, I think, Mikin and Dush in around 86 as a model for several chemical processes like Deutsch. All right, thanks. Electropolishing, corrosion, and yeah. And later, like, so there's a notion of addition of sets, which was invented by Diaconis and Fulton, and this turned out to be a special case of that. And this was done around 91. Okay. So this is like a one particle version of that. So, and popularly this is done on the square lattice. So, and mu1 you should think of in this example as being the Dirac mass at the origin. So I'm going to always start my particle at the origin and look at what happens on the square lattice. So the first particle stays at the origin because there was nothing there. So the cluster at time 1 is just the origin. Then I start one more random walk. Suppose it picks this edge. So you have these 2 points at time 2. You keep doing this. You have size 3 and size 4, so something like this. So at time t, you will have exactly t vertices on the lattice that you are occupying. Okay, so there's one more. Okay, so this is an idealic cluster growing on the square lattice, and this will run for, this is about like 3,000 particles. So you see that it's roughly isotropic, so it's almost circular. And there's some, okay, still not circular yet, but like if you run this for long enough, it will be, and the boundary is something that has some fluctuations, but not much. Okay, so it's roughly growing like a ball. Okay, so some comments about this processes. So like I said, so ideal at time t is exactly of size t. So if your graph is finite, then and of size n, then ideal is not interesting anymore after time n. So it's usually studied on infinite graphs, and questions that people ask are about what the asymptotic cluster shape is like. And once you understand that well, then you can ask finer questions about what the boundary is, what are the fluctuations. Yeah, so you can ask what the cluster is, whether it's like a ball, and what the boundary is once you understand the first question well. Whereas erosion makes sense on a finite graph for all times, and it's a Markov chain, so you can ask all the basic questions about Markov chains are still relevant in this setting. So you can ask what its equilibrium measure is like, what is the mixing time, etc. Okay. So some references to what has been known about ideal. So the first rigorous proof of the fact that this actually looks like a ball in some sense was by Lawler, Bramson, and Griffith around 92, and they showed that if a cluster has size n, then the right radius to look at is r such that pi r square is n, because you want to conserve area. And they showed that the ball is within r1 minus, up to a multiplicative factor of 1 plus minus epsilon, the ball is going to be within that cluster with high probability. But then subsequent improvements were made, like first by Lawler himself, and then two groups, one including Lionel, Scott, and David Jerison, and there was another competing group, and eventually, so there's now a very, very precise. Yeah.
Oh, so you said Scott, but there may be more than one Scott who works in this field.
Yeah, right. So Lionel, Levin, Scott, Sheffield, and David Jerison in one group. The other group was Asela and Gaudier. And now they sort of really understand what even not just the order of the fluctuations, but what the scaling limit is. So there's very precise understanding of this process. And there's another setting which is even more relevant to the case that we are talking about, is when you have ideal A, but like there are now multiple particles. So you still have, say, the infinite graph, so you have infinite room, but there are still particles of various kinds which are trying to occupy your spot. So for example, like suppose, so the ideal I was starting my particles only from the origin, but now you can say pick 2 points and minus 1 and 1, and they say alternately like emit red and blue particles from them. They will not try to kill each other once they meet. If a red meets a blue, then it will keep walking till it finds an empty site. So you will always stop when you find an empty site. And so here is a picture of what an ideally with two sources look like. So the center of the disk are the sources, and you emit these particles, and the colors sort of represent the points that the particles came from. So you have these two sources. So the purple and the green are the places where the particles only from the center of the disk occupied, and in the intersection and the outside, you will have particles from both colors. So there is some, so there are some rules about, so the particles are exchangeable. So once both particles land here, you can choose which one you want to make them walk again. So the red and the sky blue portion are regions where you will have particles from both sources coming.
What's the difference between the light blue and the red?
So here potential, these are the two regions where you can have particles from both sources occupying.
But again, why are there two regions?
Because so if you emit say n particles from here, n particles from here, they will, so you can first make them walk. They will walk like independent ideal A. So they will have these two balls. So the overlap of the sides will be exactly in the intersection, and then you can choose which one you want to make them walk again, because these sides typically will have now two particles. Right.
Again, what's the difference between light blue and red?
No. So there is no there is no difference in the sense that if you run ideal A independently, they will first. So depending on what time you occupy the sides.
You're generating the two-source cluster in a certain order. First you make a one-source cluster, then you make another one-source cluster, and then you take care of the overlaps.
Yeah, so depending on what time you occupy the site, this will, But potentially because the particles are exchangeable, you can, does not matter which particle is occupying which side. Okay, so this is still on the infinite graph, and you have two sources. And now we will sort of switch back to erosion, and so we've defined erosion on general graphs, but now we will, for the rest of the talk, we will talk about very special graphs, which are sort of approximations of smooth domains. So like the disk, you discretized it, and I will define what smooth means in our talk. And at this point, I should also remark that we studied this process on a similar but different setting with Jim and Lionel. So the main result of this talk will be joined with Yuval, but there's a different but related setting which studies the same process, and that was joined with Lionel and Jim as well. Okay, so what is the setting? So think of a smooth domain. By smooth, I will mean something which I'll state precisely, and look at the discretization of the domain using very fine mesh. So say 1 over n z2. So think of this as being embedded in the complex plane, and look at the intersection with 1 over n z2. And look at the part of the graph inside it, by which I mean all the edges that are completely inside it. So all the points which are in the interior of the domain and the edges induced by them. And the class of domains that we will work with will have analytic boundaries, which means they have local power series expansions, and equivalently, like the Riemann mapping theorem guarantees that these domains will have maps going to the disk because these are simply connected domains, and in fact the boundary will be so smooth that the maps sort of will have analytic extensions across the boundary. And for the moment at least, so the setting will be still like the sources will be like still point masses on the boundary. So you have a domain, take 2 points x1 and x2 on the boundary, they will be roughly your sources, and the graph will be the intersection of this with a fine mesh. Of course it's still like little informal because these points need not be lattice points and need not lie on the graph, but like roughly this is going to be the setting.
When you talk about extending across the boundary, you're saying you can extend to an open set that contains.
Yeah.
Okay.
So yeah, so you have this domain U and the disk D. So there are open sets U1 and D1 containing U and D, so that the conformal map from U1 to D1 restricted. Okay, good. So all right, so summary of the setup is the graph is UN, which is U intersection 1 over NC2. And so now I have to give a number k, right? So for erosion I needed a graph, I needed 2 measures, and I needed a number k, which was a set of size of the blue cluster. So this is going to be a constant fraction of the number of vertices. So I fix an alpha between 0 and half, and number of blue vertices will be alpha times the size of the graph. So that's going to be the setting. And again, like I said, mu1 and mu2 are roughly like the Dirac measures, but they still need not be lattice points. So okay, so the basic question is, how does the blue region look once you run this chain for long enough, and with your sources x1 and x2? So on the disk we saw that the blue vertices sort of accumulated near the blue source and similar to the red vertices, and there was some interface, and the limiting interface like it was roughly like an orthogonal circular arc. And the basic question is, what is the truth for general domains? So what happens for general domains? And so there is some connection to this process with reflected boundary motion, which I will make like more precise later, but like, and it's sort of well known that conformally reflected boundary motion is conformally invariant. So and here we are talking about reflected boundary motion with normal reflection. And so this led to the conjecture by Jim, which is that understanding the process on the disk sort of suffices, that if you want to understand what the process looks like on a general domain, I mean, like, so the final picture should be just the image of the final picture on the disk under some map. Now, one comment that I want to make here is, remember that the blue was like alpha fraction of the total region, and conformal maps don't preserve area. So it's so one has to make precise what this means. So, but roughly a picture like this should be true was the conjecture, and the goal of this talk is to show that this is true. So are there any questions about?
Does this also hold for the details of the interface, or this is for the?
Yeah, so we'll see what we will see what we prove, and then so the interface is because one has to even prove that there is an interface. I mean, like, so right. So your question is whether the properties of the interface also carries over, right?
Yeah.
So first one has to prove that there is an interface. So that is not provable at this point. So we don't know how to prove that. I mean, like, so we don't know how to prove that. Yeah.
Sorry, you don't know how to prove what?
That exactly a picture like this is true. That there is so everything here is blue and everything, and so there is a particular interface, and that carries over.
In the initial state could be just like a checkerboard of red and blue, and then there's no well-defined interface.
Right.
You have to show that over time you move towards something where there does appear to be a well-defined interface.
But you're saying you at can't this, prove that.
Uh,
are you saying at this time in the talk, or the?
Yeah.
No, so we will see. So we will see what exactly the main result is, and then it will. So we will see what exactly the main result is and what it exactly confirms, and then we will see.
But it's not.
There's more work to be done.
Keep
going.
Right. Okay. So the modified setting will. So throughout till now we were talking about these two sources which are points on the boundary, but like there will be some convergence issues. We will sort of take the mesh size go to 0, and so it will be technically convenient, and so the main result will be sort of in this setting where instead of having point masses, the two random walks, the mu1 and mu2, will be sort of uniform measures on small disks. So you have these points x1 and x2. We wanted to start random walk from x1 and x2, but for technical setting, like we will take two disks of radius say delta near x1 and x2, and mu1 and mu2 will be uniform measures on all lattice points inside those disks. So fix a small delta, take two disks and look at all lattice points inside them, and the random walk will start uniformly from those.
I don't understand the second clause, and also a distance about delta.
Yeah, so this is a smooth domain, so you can fix a small delta, and then you can choose for any delta small enough, you can choose disks which are say at distance delta by 2 from the boundary, and also radius say delta by 4 or something. Okay, so instead of starting from points, we will start from the small disks. And then the main result will sort of involve sending the mesh to 0, the size of the mesh to 0, followed by sending delta to 0, so that we asymptotically sort of recovered these point sources. Okay, so we need some notation. So you have the disk, unit disk with these 2 points I and minus I, and you have this general domain with arbitrary points x1 and x2 on the boundary. So the Riemann mapping theorem guarantees that there exists conformal maps going from the disk to this domain, so that I is sent to x2 and minus I is sent to x1, and phi and psi are going to be inverses of each other. And just worth mentioning that there is no unique such pair, so because a map is uniquely determined if I specify the values at 3 points. So here I am just specifying the values at 2 points, and so this is actually a family of such maps. So I will just choose something arbitrarily, and yeah. Okay, so and so now so for the disk I had this orthogonal circular arc, and they sort of have this sort of equation. So they turn out to be the level set of this function log z minus I over z plus I. So every orthogonal circular arc which is symmetric with respect to minus I and I will be the set of z inside the disk such that this is equal to beta for some beta on the real line. And now I want to define a corresponding thing for a general domain U. So I just transfer via the conformal map. So I have this disk. This is the orthogonal circular arc corresponding to beta. I call this region d beta, and then I just look at the composition with respect to phi, so which will give me corresponding regions on the general domain U. And note that this parameterization of beta depends on this conformal map. So this was what the value of this function on the geodesic on this curve is, and however we are interested in area, right? So we started with alpha fraction of the area being blue. So you want to sort of find the beta which gives you alpha fraction of the area. So this we call U alpha is U beta for the value of beta which has fraction alpha of the area. As beta goes from minus infinity to infinity, you covered the whole region, so you can find such a beta. And like I said, so this area is not preserved, so phi of d alpha is not necessarily U alpha. Of course, for a particular value of alpha, you can choose your phi to be such that this is true, but does not hold simultaneously for all alpha. Yeah, so this is going to be my U alpha. So I pick my beta so that the fraction is alpha. Okay, and I need my last notation. So I'm interested about the set of blue vertices. I want to pass from the set of vertices to the region. So I look at union of all boxes around the blue points. So I have this set of blue points on my graph. I look at all boxes of size 1 over n which is centered at those points. And this is a statement of the main result which says that, so you have this set U alpha, you have the set of blue vertices, you look at the region version of that, look at the symmetric difference and take its area, and the expectation of that under the stationary measure of this chain sort of will go to 0 if you send the mesh size to 0 followed by delta going to 0. So if this blue region here take the box version which is a region on the plane, take the symmetric, and you have this region U alpha which we just defined, take the symmetric difference, look at its expectation, and then that goes to 0 if you send n to infinity followed by delta to 0. However, there is some technical requirement, so we sort of need n to go along powers of 2 to infinity. And this is because some of the proofs here rely heavily on the fact that random walk on these graphs UN converge to reflecting Brownian motion on the domain U. And the results that are known in the literature uses the fact that that sort of convergence is true only if n is a dyadic power of 2. Of course, I've personally spoken to the co-authors of, to the authors of this paper, and they sort of believe that it's true for the entire sequence n, but the results that appear in the literature uses this assumption that n is like 2 to the k. So in words roughly, if the sources are small enough, which means delta is very small, then if the mesh size goes to 0, then at stationarity the blue region looks like the set U alpha in the sense of symmetric difference. So the area of the symmetric difference is small. So that's roughly the statement of the result. So is this clear what the theorem is proving? Okay. So a remark here which might not be a priori clear is that this chain has a well-defined stationary measure. So it's not irreducible, but still there is one recurrent class, so you can still well define the stationary measure. And also, because it's a finite system, even though at equilibrium most of the time it will look like there is an interface, and the interface is sort of like this image of the circular arc, which is the geodesic, there will be a positive fraction of time where it will look something very weird. So I mean, like, it does not have to look like this always because it's a finite system, so this has positive probability of happening. So it will sort of happen like at a positive fraction of times, even though like very small probability. Okay, all right. So these are some of the initial comments, and so now let's see why one can expect this to be true. Why you can expect the interface to be like a geodesic. So if there was, say, an interface, then it should have some stability property that. So red random walk would start from the top, and like it will stop when it hits the blue side, and similarly a blue random walk would start from the bottom. And so if this interface has to stay in place, for every point roughly the push from both sides should cancel each other out, right? So and the push is nothing but the harmonic measure starting a random walk from here, right? So you start a random walk from here, you look at the chance that it hits this point, and that should sort of agree from both sides. This is one of the properties that like if there was some interface, it should have a property like this. And okay, so now first we have to sort of find a candidate which has this property. So okay, so here is where the conformal invariant nature of reflecting Brownian motion comes into play. So it will turn out that geodesics will have this property, and a way to see this is so you can think of Brownian motion on the half plane. Okay, so think of reflected Brownian motion on the half plane, which is very easy to define, and just by symmetry you can look at the semicircles, and the semicircles will have this property that the harmonic measure from suppose you start Brownian motion from the origin and look at the hitting distribution of a semicircle, that will be uniform just by rotational symmetry. And similarly, if you start Brownian motion, say from infinity, whatever that means, so from far away, it will also sort of hit the outside harmonic measure will also be sort of uniform, right? So for the half plane is very easy to see just by symmetry, and then because path properties of Brownian motion don't change under conformal maps, and images of semicircles, so if you take the half plane to the disk, the images of the semicircle will exactly be these geodesics. And so this fact that is easy to show on the half plane will sort of imply that even on the disk, the right curves which has this property will be this geodesics.
It doesn't look like a geodesic. It should be perpendicular.
It should be perpendicular here. Yeah. This is a hand-drawn picture, so yeah. Okay. So geodesics have this property that harmonic measures sort of cancel each other out from both sides. Okay, so this is one candidate for the interface. And now you have some self-correcting things. So if you have some other interface which is not like a geodesic, then you can argue that the part which is below this geodesic, this blue curve say, will have net harmonic measure pushing it up. So the harmonic measure from the bottom will actually exceed the harmonic measure from the top, because they sort of are equal on this geodesic, so you can argue that here they will sort of be more from the bottom. So there will be a net upward push in this part of the curve, and similarly a net downward push on this part of the curve, right? So if you didn't have the geodesic to start with, this sort of heuristic tells you that you will sort of eventually sort of push yourself towards the geodesic, right? So those are sort of the right candidates. Now, again, like I said, so interface, the notion of interface is not, does not exist for all configurations, right? So only if all the blues are like near the source of the blue source, and if all the red points are near the red source, then only you can sort of expect to define an interface. For example, like in a configuration like this, so even in each source, you will have like both red and blue particles. So you can still define an interface maybe, but like, so it's not like it will separate the two sources, right? So if you have a small disk here, a part of it is red, a part of it is blue, and similarly the other side, so you will not have an interface which sort of separates the two sources. it will sort of like it can cut through the middle of a source, right? So we'll sort of not take this approach directly, but like slightly different, which sort of tries to quantify this idea. And that would sort of involve something called the green function, which I'll define in a bit. All right, so here's one more sort of heuristic in the same direction, which is, okay, so I'll define what Green's function is in a moment, but like let's just go with this. So it's well known that, okay, so you have this graph here. I'm still working with the setting that there's an interface, even though I said that the whole problem of making this formal was because there was no interface, right? And so you have this graph, and there are two regions, say the blue and the red, and you can define something called the green function on the whole graph and on the two graphs individually. So you can look at the blue part, you can look at the red part. So there are two green functions that you can define, and it will turn out that the Laplacian, whatever. So I'll not. So this is like an informal thing. So it turns out that the Laplacian of the green function here is the harmonic measure at this point, and similarly for the red one, it's harmonic measure at this point. And we said that this interface should have the property that the harmonic measures should cancel each other out. So you will have some condition like this, that the blue green function minus the red green function should have Laplacian 0 on the boundary. And of course, they are also harmonic in the blue part and the red part individually, except for the sources. So ignore the sources for the moment. So what you end up with, this difference of the green function is sort of harmonic everywhere except these two sources. And the actual green function on the whole graph also satisfies the same property, that is also harmonic everywhere except the two sources. So this difference of green function has the same Laplacian condition as this green function. So you have this. So this is the green function of the whole graph. This is the difference of the green function. They have the same Laplacian condition, which means that the difference is the harmonic function. And harmonic function on bounded graphs are constant. So these are same up to a constant, which means and notice that. Okay, so I did not mention this, but like these two Green's function are also sort of vanishing. So the blue Green's function sort of vanishes on the red region, and the red green function sort of vanishes on the blue region. So on the interface, both of them are sort of like 0. So you have this, so Gn, this function is roughly like 0 on the interface. So Gn is roughly like a constant on the interface. And the blue region was one side of the interface, so it's reasonable to believe that the set of blue sites is all points where gnx is bigger than some constant. So gn was constant on the interface. On one side it was bigger than the constant, on the other side it was smaller than the constant. So roughly the blue region should be occupying a level set of the Green's function. Okay, good. So these are two heuristics sort of involving the harmonic measure, but this one uses Green function and the fact that derivatives of the Green function are like the harmonic measure near the boundary. Okay. Good. So this sort of gives you an idea of what the blue region is. So it's a level set of a certain function. Okay. So all right. So now we'll state a quantitative version of the main result, which will imply this. So we had this result which said expectation of some area was going to 0 if I took these limits, and now we'll have a quantitative version of that result. So I need some notation. So okay. So look at all configurations, which is almost like what we want it to look like. So there are only a few blue particles in this region where we want it to be all red, right? So and this quantifier is, so you only allow at most epsilon n square vertices of this type, which is in this region U alpha complement and has blue color, or is in U alpha and has red color. So at most epsilon n square particles are colored opposite to what they should be. So they are separate from the geodesic and has the wrong color, because they're falling in the wrong region. Okay, good. And so for any such configuration, the blue region and U alpha, the symmetric difference is at most, has area at most epsilon, because there are just epsilon n square particles on the other side. Okay, so if I show that the measure of this set is large, then I'm done, right? Because I want to show that the expectation of the area goes to 0 in probability. Expectation of the area goes to 0. It suffices to show that this thing goes to 0 in probability. Area of the symmetric difference goes to 0 in Okay, so this is the formal statement. So okay, you can forget the quantifiers. So take a small delta and a large n depending on epsilon, then this measure of this set omega epsilon is 1 minus e power some constant times n square. Okay, so I have this epsilon fixed, then for a small delta and n large enough, the stationary measure of this set is 1 minus exponentially small in n square actually. And then this automatically implies, because this is epsilon was arbitrary, I will send epsilon to 0. Okay. So proving this suffices. Okay, so the key tool used in the proof is identification of a certain function. So this will have these two properties that I want to show that omega epsilon is a large measure. That is what I want to show. So I identify a function w on the space of colorings, which is maximized in omega epsilon, and when it's outside omega epsilon, it sort of increases on average. So you have the state space of all colorings, you have the set omega epsilon that you want to show has large measure. I identify a function which is maximized inside that set, and whenever it's outside, it sort of increases on average, which is what this means. So if you start from something which is outside omega epsilon, then in one step the value of the function increases. And this implies that, this should imply that you, no matter where you start from, you should hit the set omega epsilon quickly, because the maximum is inside this set and you cannot continue increasing forever, which you will do if you are outside this set for all times. Okay? And to motivate the construction of this W, recall that the heuristic that I discussed says that the blue region is roughly gnx bigger than k for some k. So all the blue particles should be in this region gnx bigger than k for some k, right? Which means, okay, which then sort of gives you a natural candidate for this, what this W should be on the space of colorings. Okay, so before doing that, I'll define formally what, I mean, like semi-formally what Green's function is. So it's harmonic everywhere except blue and red sources. You have these two disks, it's harmonic everywhere else, and the Laplacian is sort of 1 and minus 1 on these two sources. I mean, I'm suppressing some constants, so I actually don't want 1 and minus 1, I want it to be something else, but up to constant this will be the function. And the rough formula is you sort of, so xt is say the random walk on the graph, and then you basically look at the time that the random walk spends in one source minus the time it spends on the other source. Now this integral goes from 0 to infinity, so individually these two integrals are infinite because both of them have positive measures, so random walk will spend infinite time in both of them, but the difference is sort of integrable because these two disks had the same area. So what I'm saying is that you look at the expected local time in one source minus the local time in the other source, and that will have these properties. So the Green function that I defined in, I was talking about in the heuristic is going to be this function. And then the heuristic said that the blue region was roughly a level set of this function. Okay, so which means that a natural candidate for W should be this function, that is some Gn to be some Gn over all the blue sides. So you have some coloring, you have some function on the graph, and then you look at the sum of Gn over all the blue sides. So I said that the W should have these two properties, that W is sort of maximized in omega epsilon, and that it increases on average when you're starting outside. So these are the two things that are actually like constitutes the main body of the work. So it's these are technically challenging things to prove. Sorry?
First one is challenging?
Yeah, because so I defined my set. Omega epsilon was defined in terms of U alpha, right? And U alpha was defined in terms of this log function, right? And here I have a discrete Green function, so you have to show some convergence. Okay, so like I said, so you have to show something like this is true, that roughly Gn, if n is large enough, then roughly it looks like this function. Okay, so so it will. All right, so do you remember what psi was? So you have these domains D and U, and psi was the map which went from U to D, and this was exactly, this bigger than beta was exactly the region U beta. And if Gn is, okay, so and the proof sort of uses the fact that random walk on this graph Un converges to reflecting Brownian motion on U, and you have to sort of use the fact that reflecting Brownian motion has some nice differential properties. So it is a solution of a well-known PD with some Neumann boundary conditions. So so you use the fact that reflecting Brownian motion satisfies some PD and the fact that the random walk hit kernel converges to the reflecting Brownian motion hit kernel. And this sort of convergence uses, the things that we use are actually very recent results about local convergence. So the fact that random walk converges to Brownian motion is not very old, so it's pretty new. And the fact
that random walk converges to Brownian
in this reflected setting
is new.
Yeah. So if you have a domain and do random walk on that, it will converge to reflecting Brownian motion.
I thought that was classical.
No. Random walk converges to Brownian motion could be it depends on what your timeline for classical
That
is.
was part of my intuition back in the.
Of course.
So it was conjecture.
But proving thing is Mm-hmm.
I thought Yuval told me this. He told me it's.
Yes, but in special cases here.
For example, on the half plane, it's easy to show. Okay, and so there's a very recent paper which sort of proves quantitative bounds for this convergence. So they show local CLT estimates of this convergence, and this is what one can use to show that this discrete green function, which was defined in terms of the random walk, actually converges to this continuum function on the whole domain. And then you again use the fact that this hit kernel for the Brownian motion is a solution to some PD. Okay, so what does that imply? So we had this W coloring which was summation of GNX over the blue vertices. You said that GNX is roughly like this function. So which means that this region was roughly the region where this function was less than beta and this function was bigger than beta. And Gn is now like this function, so Gn bigger than beta and Gn less than beta are roughly the same regions, right? So this region U alpha was defined in terms of this function being bigger than some beta. But now I show that Gnx is also roughly like that same function. So U alpha is roughly the region where Gn is bigger than beta. And so to maximize W, you want to pack in all your blue vertices in this region. I'm summing Gn over the blue vertices. I want to maximize it. This is the place where Gn is bigger than beta. It has alpha fraction of the whole area. So I should put in all my blue vertices in this region to make W maximum. Okay, which means that the maximization indeed lies in the set omega epsilon, because you cannot allow too many blue vertices in this region for it to be maximum, right? Okay, so this was the first claim that this sort of is maximizing omega epsilon. I still have to show this positive drift condition that if you're outside, then you increase on average. Okay, so this sort of uses an energy argument. So look at this graph. Look at this blue region on this side. Look at the red region on this side. So now you have three graphs. One is the whole graph, one are these two colored graphs. And so now look at the effective resistance, which I'll define in a moment, for this whole graph and these two other graphs. So you have these three effective resistances for these three graphs, and it turns out, I'll define shortly what this effective resistance is. It turns out that this difference is exactly the effective resistance of the whole graph minus the sum of the effective resistance of these two small graphs. So you have this blue region, sorry?
Exactly that.
Okay.
In a discrete approximation.
I mean, it's not because so the interface is not like a line. So you have these two regions. So the red hit, so it's not exact, right? So there is some error, small error here, but like roughly, and the small error is polynomial is small in n. So it's 1 over n to the some beta or something. But roughly this is true. Okay. So let me define what effective resistance is in this setting. So these are not point sources. You have these two small disks, and you start your random walk from the disk, and you stop it till you hit. So you have these two small sources which are not points, and effective resistance of the whole graph in this setting is the energy of the unit current from the blue source to the red source, such that the current through each starting point is 1 over the total number of sides. So roughly, you have some current flow going from the blue source to the red source. That will give you some energy on the whole graph, and effective resistance of the whole graph is that energy. And similarly, for the blue and the red regions, the energy of the unit current from the blue source to the interface will be your resistance for the blue part, and similarly the red part. So you have these three graphs. One of them you have these two sources, so you send unit current from one source to the other source, compute its energy. For the other two, you have a source and an interface, so send unit current from the source to the interface, compute its energy. And And Thomson's principle sort of says that if you look at a graph, look at any flows, then the energy of the flow, which is the minimum energy of a flow would be only when the flow is a current itself. So currents sort of minimize energy among all flows, and so then you can see why this thing should be non-negative at least, because if you take the flow which is on the whole graph going from one source to the other source and restrict it to the blue part and the red part, they will give you honest flows on them which has the same divergence as this current flow. So they have strictly more energy. I mean, like, they have at least as much energy as these ones. So RF should be at least as big as the sum of these two, because RF restricted to blue is bigger than this, RF restricted to red is bigger than this, and these are sort of disjoint sets. But then you can actually prove some quantitative lower bound if you started from something which was away from. So if you had this initial thing that there were at least epsilon n square vertices on the wrong region, then you can actually prove a quantitative lower bound. This is not just non-negative, but it's bigger than some constant a depending on epsilon. So if you start from omega epsilon complement, you will have some positive drift which is lower bounded by a function of epsilon. Okay.
So I guess I thought that the effective resistance would be smaller than the sum of those two.
Why? These are disjoint graphs. So yes, so I look at the energy of the flow from going from here to here, and I look at the sum of these two, which is the same as shorting this curve. So I should think of this as one point, right? So what is the sum? The sum is the effective the energy of the current going from here to here if you glue all these points along the boundary.
It's like series, you're connecting things in series.
And because this,
if you short out the boundary, you make the resistance less.
Okay.
but so and you will.
No,
So,
it's the same potential along the whole boundary, so shorting it out.
no. So this is some
That's why
arbitrary interface. So
Oh.
if this was the same potential, then this would be 0. But the fact that you're starting from omega epsilon, outside omega epsilon, tells you that this interface is not of the same potential, so you actually make some quantitative gain, which is this a epsilon. Okay. And so now, so I'll quickly say how these things will imply the result that we wanted to prove. So so you have this function w which increases on average when you're outside, and the maximum is inside this set omega epsilon. So this should imply that the hitting time of that set should be small. So the first result is that the hitting time of omega epsilon, no matter where you start from, is going to be like order n square. So it's being bigger than Cn square is has exponentially small probability. So suppose this is your state space of all colorings, and omega epsilon is a small set inside. You start from anywhere, in order n squared time you hit the set omega epsilon, right? So this is just in words what I just said. But to show that the stationary measure of this is close to 1, you also have to prove that once you enter this set, you don't escape quickly. So this is the next step, which is that once you reach, so you first hit omega epsilon, then you carry on and hit something smaller, omega epsilon prime, and once you're in omega epsilon prime, then it will actually take you exponential time to get out of omega epsilon. Okay, so these are just submarginal conservation bounds. So the function w of sigma t as t runs is a submarginal, and so you have conservation bounds that will sort of imply this. And this is the same argument that you have for a biased random walk. Okay, so now we have to relate. So we have the hitting time results, and then we have to translate that to stationary measure. Okay, so this is not very hard. So stationary measure is the amount of time that you spend asymptotically in a set. All right, so you start from anywhere and you look at, and you want to measure the stationary measure of a set, and you look at the proportion of time that it spends in that set. And the hitting time results show that no matter where you start from, in order n squared time you will hit the set omega epsilon, and it will stay there for an exponentially long time, right? So you typically spend only order n squared time outside omega epsilon per time interval of exponentially large length. So this tells you that something like this is true, that the mass of omega epsilon is bigger than 1 minus some. This is exactly the proportion that you spend outside. Okay, so the proof of the quantitative result is complete, which then implies the main result just by sending epsilon to 0. Okay, so now I'll quickly wrap up just by making some final comments that the main result was in terms of this area of the symmetric difference, right? And in the picture, in the simulation, we saw that exactly there were like no red particles in this region U alpha. So there was some interface, but there were absolutely like no red particles in this region. So in joint work with Lionel Levin, Yuval, and Jim, we managed to prove this result in a slightly similar setting, but like which had a simpler geometry. So the setting was, we studied this process on the cylinder. So you have the cylinder, and now the sources are the top and the bottom. So the random walk starts uniformly from the top. The red random walk and the blue random walk starts uniformly from the bottom. And there we could actually show that under equilibrium, so this, and because of symmetry in one coordinate, this should be the interface because there's nothing going on in the other coordinate. So the blues should, so if the blues were like alpha fraction, then the right height should be alpha if this height is 1. And then we could show that if you look at the region which is outside alpha plus minus epsilon, then with high probability there would be no blue particles in this region above alpha plus epsilon, and there would be no red particles in this region alpha minus epsilon. But we crucially use the fact that some things were very, very precisely known on this geometry, which is not true for general domains. So yeah, so we use the fact that IDLA was very well understood on cylinder. So first we proved a similar statement for the cylinder that there would be some dust particles, but like very small, and then we used some precise estimates to show that those will be wiped up very quickly. Okay. So a relevant question in this setting would be to prove such a theorem for this general context. So have any general domain and show that even a picture like that is true even in this setting. And once you do that, then the next question would be to understand the interface better, like people did for IDLA. So once they showed that this was roughly like a ball, what was the interface going to be like? And because you have forces from both sides, it's believable that the fluctuation should be even smaller than what happens for IDLA. So for IDLA, we know that the fluctuations of the boundary is like logarithmic, so it should be even at most that much. And then you can ask the question in high dimensions for general domains. And the correct intuition would be again this green function intuition, which says that the separating hypersurface should be still a level set of of a suitable dipole potential function on this region. And then you can ask a question. So throughout this talk, we were working with two measures which were separated from each other. But then you can ask the other extreme, which is what happens if both the blue and the red random walk starts from the same source. And now suppose you have the infinite lattice, so you have Z2, but the model is you alternately release red and blue particles from the origin, and they will keep walking till it finds a site which is either empty or of the opposite color. So a blue walk can hit a red guy or an empty site. In either case, it will turn it into blue. So it will treat white and red as particles of opposite color. And it turns out that even though you have like released like 10 to the 10 particles, only like a few thousand sites which have been occupied. So most of the activity would be like red trying to eat up blue, blue trying to eat up red. So you will rarely like fill up these empty sites. But nothing is conjectured in the setting. What is the picture like? Okay, so this is one, and then you can ask the question about what happens if you have multiple colors. So this is a simulation where you have like 3 colors, each of mass 1/3, and the sources are the roots of unity, and then you run it, and this is what it looks like. But if you did not start from the setting where every color was equal, and you have, so remember that in the talk we had these 2 sources. We took a conformal map. So those map to so 2 sources on one domain would map to 2 sources on the other domain, and then we had this one more degree of freedom which said that you could map this region d alpha to actually u alpha using. But here, once you fix these 3 sources on 2 different domains, you have no control on what the areas are going to be like. So you don't exactly know whether a conformally invariant picture is sort of true here, and what exactly is the truth in this setting. Okay, so I think I'll stop here. Thanks.
You said that in IDLA the fluctuations are logarithmic. That's just bounding largest fluctuation, or is there any understanding of what a limit is with log scaling?
Yeah, so it's very well known, and so you should probably ask Lionel because he was one of the. Yeah.
So in 2 dimensions, so the largest fluctuation is logarithmic, but typically we think they're like the square root of log, and there's a limit which is a close relative of Gaussian free field.
That's known?
Yeah, I mean, you can always try to strengthen the results. You know, it's known for a certain class of test functions that it
Yes, I
converges.
see. Okay. Yes, so you get the answer is you're getting Gaussian free field.
It's not quite Gaussian free field because the
somehow-
origin is special,
Huh?
but the origin is a special point.
Yeah.
So we call it augmented Gaussian free field, but it's very, very close to Gaussian free
In
field.
space, okay.
That Gaussian field is with no normalization.
Right.
Is what?
No normalization. The fluctuations themselves are tight. At any point it's tight. Only the maximum gives you the log.
In 2 dimensions, you get root log.
Or you get root, so there is a root log normalization.
I think this might be a difference between Gaussian free field and augmented Gaussian free field. So
So you had a question, right?
in higher dimensions, if the fixed direction is tight.
Was there something that went wrong if you had the sources being single vertices?
Right. So first of all, the green function order is more, right? So a point will, so if you start random walk from a point, it will be hit like more than, so like roughly like log n times. So if you stick random walk starting from a point and kill it on the other point, and this convergence result does not hold because Brownian motion does not hit this point, so we could not make that work. That if you take this discrete green function and then what will be the limiting behavior of that? How to show that that actually converges to something like this log z minus I over c plus I. But one approach could be just without bypassing all this Brownian motion convergence. So you can start with this function log z minus I over z plus I, which you know is harmonic and has a singularities and has Neumann boundary condition on the continuum, and like restrict it to the lattice. So it's not going to be exactly harmonic. So it's going to have some error, and then you can show that even with, so I had this weight function which was, I was summing this gnx over blue sides, right? So instead of summing gnx over blue sides, you can take this actual continuum harmonic function and then just sum that over blue sides and show that that works. So I have this function gn, I show that gn converges to some function log of something over log of something over something, right? But you can start with this log of something over something directly instead of having the discrete green function. Then it will not be exactly harmonic, you will have some errors, and then but just show that you will still have this positive drift condition even in that case.
But that still incurs some technical.
Right, of course, yeah. So this will be a robust way because this sort of convergence of random walk to Brownian motion is only known for square lattice, right? So.
But this still incurs some technical.
Oh yeah, of course, yeah. But like, right, sure.
I just want to mention some of the motivation behind what I was doing in 2003, which was I was very interested in rotor routers and what they might be good for. So I was trying to come up with probabilistic questions for which this kind of de-randomization would give a close match. And in fact, this is an example of that. So you can do this kind of competitive erosion in a de-randomized sense. And if you do it the right way, you get the same interfaces, being the level sets of Green's functions, conjecturally.
By right way, you mean just doing rotor walks instead of random walks, or do you have to do something
here's
else?
the thing I always forget. I could look it up in my notes and find out which is which. There's 2 obvious candidates for how to do rotor walks, depending upon whether the red particles and blue particles use the same rotors or
I see.
different rotors.
I see.
And one of them gives you the interface you expect.
Oh, the other one
The
does
other
not.
creates macroscopic disturbances of the interfaces. I never understood it, and I can't remember which one was which. But if anyone's interested in this kind of
So I
stuff,
would imagine the independent rotor walks would sort of give you, if you use 2 different set of rotors for the 2 walks, then probably it should mimic the random walk closely, right? I mean, it's not clear.
I guess would be the
Oh, opposite?
The reds should spin the rotors backwards from the blues.
I never tried that. Maybe that would be the way to do it. I used the same
Pictures?
direction for both of them. And it basically, one of them, you could definitely see there was a kind of a skewing, a clockwise skewing of the interface in a very
see.
systematic way.
Do you still have pictures of that?
I could dig them up, I think.
So that's right. So it would be nice to prove, especially as there are several natural versions and only some of them work.
Yeah. The other thing I'll mention is that I did an experiment with 3 colors using the kind of the same thing you did on your last slide, but where it was sort of lopsided, where it was symmetrical. And there still appears to be a meeting point where the angles are 120 degrees, which is a sort of a natural thing.
But how did you arrange to keep the mass equal? Did you? So
No,
what
the
was
mass
the
wasn't
rule?
equal, the areas were unequal.
No, but how did you arrange to keep it unequal?
So what was the rule? So you,
What was the rule? Each time did you?
I
go
believe
round
the rules
robin?
you just cyclically alternate between them.
That should equalize the mass.
Sorry?
That should equalize the mass.
If you introduce a red particle and then a blue particle and then a yellow particle,
Because each time it captures something of another color.
Mhm.
Suppose the reds are in a minority,
Mhm.
right? Then when, so when it's their turn, they grow by
I
one.
remember now, yes. It's the particle that just
Uh-huh.
captured.
Okay,
That was it.
that's the right.
So when red steals from yellow, then
Right.
yellow gets to
Yes.
go next. Then when yellow
Uh-huh.
steals
Sure.
from,
Right,
I'm pretty
that's-
sure that
that's-
was it.
Yeah.
Yeah, that's the way to keep it
Safe.
Yeah.
otherwise it just drifts to the middle.
Anyway, the pictures are part of a Mathematica notebook, so we could see what the code does, but I'm pretty sure that was it.
We just went through the same realization some years later. Any- Let's thank